Okay, before we proceed with our small subtopic there, let me recap a bit what we have gone through yesterday, especially for the counter. We just discussed yesterday about counter. There is asynchronous and also synchronized, and the big differentiation between each other yesterday I mentioned is about the clock. When you have this same source of your clock, then you're going to have the synchronized. If you have different on the clock, source is going to be asynchronous. This is the first thing that you can see to differentiate between asynchronous and synchronized. Okay, this one you can read it. And yesterday we already take a look. There is if it is under counter, normally it's going to be calculate follow on sequence, but sometimes you can also having jump here, jump there. You can see from 0 to 1, from 1 to 3, from 3 to 2. It's depend on your condition. And where you're going to apply your counter, there is a lot of scenario that you can apply. Yesterday we discussed it already. And there is 4 characters of counter that you need to remember. So this must be can ask in your part A also, but sometimes throughout all of this, you need to know what the difference between asynchronous and synchronous, about the counter up, down, or random, and about modulus, whether it is transcaded or full. Transcaded and full, you can see yesterday the differentiation. Later on after this, we will go through a bit recycle or saturate. Okay, now you can see here. First point about unsynchronized and synchronized and unsynchronized about the clock. So this is the example, and I already informed you that starting at the first clock there, it's going to be your LSB. For this picture below here, your LSB to the MSB. But here it is a different because your clock is on the left. So this is LSB until your MSB here. Okay, you need to know how to determine your LSB and MSB. If you wrongly also put the LSB and MSB, your answer for the output will be incorrect. Then counting up, counting down, yesterday we already looked into, which is you can have from 0 to 1. You can see it's moving up from 1 to 2, moving up from 2 to 3. But sometimes this one normally we will have like a flow for using a follow the clock sequence. But in this picture it is anti-clockwise because actually it is from this we just delete at this part. That's why you can see it's moving like this, but it's okay as long as yesterday I mentioned we can see and we understand. Normally we will like having 0 0 and then it goes to 1 1 and then 1 0 0 1. So we have from 0 to 3, 3 to 2, 2 to 1. So it's moving down, counting down. And there is also things that you can have both. You can have both. So here is it. Now that is about sequence counting. You can also have the modulus mode. So what is the mode? Mode is depending on the stage, number of stage that you have. If you have like this, okay, I just give you example, don't look into the value. If you have this, you have mode 2 because you have 2 state only. This we can say circle. These circle are referring to one state. This is another state. So from one state to another, from one state to another. So you can see where you have two states. When you have another, then it can say that it is mode 3. So it's depend on also following the sequence, whether it's follow sequence or not, whether it is transcaded or not. Okay. Here mana dia punya ni, dia tak cakap about transcaded and full. Okay, it's okay. Another one is for the mode 9 is okay. Then repeat the sequence, counting sequence, whether it is repeating or not. If let's say you are having 1 1 here, is it having an error to continuous? If yes, then it's repeat, or we can call it as a cycle. But sometimes, as I mentioned, you have something in the scenario that you didn't have any coloration afterwards. This have after that have, and suddenly at the end of the calculation is pointing out to itself, maybe okay. But so it is not it's not a recycle because it's not continuous. See, it goes to back. Okay, next is about unscreenless counter. Okay, this one yesterday we already looked into, and I asked you to remember in this table. This table uh, a summarization for you before you can like enhance for 2 bit, 3 bits, 4 bit, 5 bit, and etc. for the counter. In terms of the positive or not negative way, you can see here you have positive age. What is defending for the positive? It is about your clock. If your clock are drawing like this, it's going to be positive, while negative, it's going to have the bubble there. So that is the only difference about positive and negative. This is the first thing I mentioned. I always repeat these things, so I hope that in your final exam you know already, and don't repeat the similar things if you have done wrong before. And then it's following whether it is counting up or counting down, and it's going to be besar. So maybe you can just remember this table. Like, okay, for counting positive age, counting up, you're going to connect to your Q bar, previous Q bar. So your positive age for countdown is going to be Q, previous Q. So what you need to do is, if you have negative, you're going to do vice versa. If counting down, counting up is going to be similar to here. You can see, you can see here. So it's going to be vice versa. If you want to have a counting up, is going to be similar to here. So after you already remember about your summarization, the basic connection that you might have, okay, the basic connection that you might have, you can just enhance how many flip-flop got after that. Also, the connection is similar. Okay, about the things on the timing diagram. For this timing diagram, what is happened? You should see the input of J and K. first J and K for this specific counter, you're going to connect to high always. Okay. And if you look for this clock, it is a positive clock. So draw the arrow here to help you to see basically where is the point that you're going to do toggle. Why toggle? Because J and K is 1. And then you draw the dotted line for the next output. Starting from 0, then you're going to toggle at the specific positive clock, and then you go until you have and meet to the negative positive clock. You toggle continuous until you are meet your next positive clock. You toggle and similar things. After that, you already done for the first flip-flop. You can see this is your output. Now you got this output already. You already got this output. So you already done. But you can see you want to move to your next flip-flop. But our C now, our clock now are depending on our Q bar. That's why we need our Q bar first, which is toggle from our Q. Yesterday, I give you example to do with your team member. Everything is connected to Q because I don't want you to take longer because yesterday is 4-bit, right? So I give you something that easier, which is when you have Q, it's going to be the next clock. But when you are connecting to the Q bar, it took longer because you need to draw the toggle for your Q bar. When you have the toggle there, then you will draw back the positive clock. Now our positive clock is here. If you forgot about this, you just assume your Q to be next clocks. You can see this is your positive, this is your positive, and you're going to toggle at here. So your answer will be wrong. You need to follow your positive clock for the Q bar. When you have this positive, and then you're going to do similar thing, toggle when you meet the positive clock. After this, if you have another one, it's going to be similar. You need to do the Q1 bar first. Toggle from this. I'm going to get like I'm going to get some sort like this. So this is my positive clock. So my Q2 will be getting like this. So next, if I have my another Q3, so what is happened? My Q3, I'm going to draw the Q bar first. Then you can see there is no positive there. I guess until the end. So it's going to be like this for my Q3. So it depends as long as you see it carefully. Okay, this is Q bar. I need to draw Q bar first. Okay. Please remember because yesterday we just do exercise together for the Q. Next is after you draw the timing diagram, after you draw the timing diagram, then you can draw the stat table. Yesterday, most of you are just drawing the stat table without referring to your timing diagram. So what is the purpose you draw this timing diagram? Untuk hiasan semata-mata. So for this, you can see here at all the cycle, you need to look into the value. Let's say for cycle 1, you got here 0, 1. Another one for cycle 2, you got 1, 0. For cycle 3, you got 1, 1. And cycle 4, you got 0, 0. So you just copy paste back and put into the cycle. So this is your stat table. So first of all, you need to draw the logic diagram. Second, you need to draw the timing diagram. Fourth, you're going to do the stat table. And 3. And fourth, you're going to draw your stat diagram. Okay, this is your stat table. After you done here, then you can move to your stat diagram. How your stat diagram? I think here they didn't share. So you have 0, 0, you have 0, 1, 1, 0, 1, 1. So you draw here. This is your initial. You can see. Then you're going to go to the first one. And then from the first, you're going to go to the next one. And then you go to the next one. That's why you have here. But when you have here, let's say, there is no this value. Or maybe you are doing only until cycle 3. So you just, this one is one. You just need to stop here because you don't know that after these 4, is it going to cycle or not? Might be you can try to check. So you check for cycle 4, what is the value? Because you can see here, there is no value that related to above. So you just stop here. That's why yesterday, I didn't give you the example for this one. For another 2 section, I give them an example for 5 bits. I asked them to do 5 bit. Yesterday you just did 4 bits, right? They are doing 5 bit until 16 cycle. So they didn't meet at the 0, 0, 0 back cycle. So most of them are doing 0, 0, 0, okay? Let's say 0, 0, 0, 0 yesterday. And then they are until 1, 0, 1, 0. And most of them are drawing this arrow. So I asked them, how are you going to relate for this, right? If you are only until here, your cycle is until 3. Do you know that after cycle 3, it's going to be 0, 0? This table, as I mentioned, although you know, okay, this is counter, of course, it's easy for you to predict. But if you don't know that this is a counter and this is just following the scenario, you cannot assume, okay? You cannot assume it's to be 0, 0 and just connect it like this. So you need to try to see what is the next cycle. If the next cycle suddenly is 1, 0, so you need to go back to here, not doing this error. So maybe your counter will be from 0 to 1, from 1 to 2, from 2 to 3, and then 3 to go back to 2, and then go back to 1. You don't know, right? So you cannot just assume before you meet here. You can see for this, when you already confirm cycle 4 is written back 0, 0, means that it goes somewhere similar to above. Okay, so you need to check basically, then you can, okay, this is going to point to here. Okay, this is your stat diagram. Okay, so yesterday we already looked into this example. For this example, it's very easy because this is just 2 bit, 2 flip-flop only. Okay, 2 flip-flop only. It's very easy for you to get the answer, especially when you can see the connection is just for the cube. So you need to draw the clock. It asks you to draw 4 cycle, then you draw 4 cycle. And you look into this. This is negative clock. You draw the negative clock there. It's help you and it's help your lecturer to check. So after you draw here like this, and what you need to do is next, you just start with 0 for the Q, 0 there. You do for the first flip-flop. And then it continues until you meet your negative clock there. You do toggle. Please make sure carefully. Maybe sometime like your lecturer is playing with you. Might be here is low. So you need to check carefully. If low, is what happened. You're going to get no change at all, isn't it? So please make sure and read the question carefully. Don't you like, oh yakinnya saya, yakinnya saya this is counter, and you did not see this is low. You just see, okay, this one is this is counter, and then without knowing it's going to be 0 0. Supposedly if 0 0, your JK will be no change, and it is going to be like direct, no change at all. Okay, so now you can see it is high. It is a scenario of 1 1, so it's going to be toggle. For toggle, when you meet the negative clock there, you're going to toggle negative clock, you're going to toggle negative clock, you're going to toggle negative clock, you're going to toggle. Finish for your first flip-flop. Now you need to move to your second flip-flop, and your second flip-flop is basically a normal flip-flop that you remember in your module 7. But this one, your clock here is not this. This clock is now referring to my Q, previous Q. So this is my previous Q, and it's going to be my C now. My C I can define is to be clock 1. So this will be the clock 1. It is still negative clock, so I'm going to draw at negative and negative. So the next changing is only at this dotted line. Starting at 0, nothing happen until you meet the negative clock here. You're going to do toggle. You meet another negative, you're going to do toggle. So you finish. What else you need to do? At every cycle here, put the value 0 0, 0 1, 1 0. Here is 1 1. After you done this, then you can move to your stat table. You just copy back everything starting from your initial, and after that you just copy paste the value at cycle 1, cycle 2, cycle 3, cycle 4. Done for your stat table. You need to move to your stat diagram following the stat table. Okay, this is the correct flow. Don't just simply, okay, I know this is by looking at this flip-flop, we said, okay, I know this is counting up positive clock, so it should be following counting up. But you wrongly get the value at each cycle. Also, you're going to get wrong like yesterday. Okay, next. This is 3-bit. 3-bit countdown ripple counter. I remember the things positive, counting up, counting down. If I have positive counting up, I'm going to connect to my Q bar. If I have negative counting down, I'm going to connect to my Q. So it will be vice versa. For my negative clock, this will be Q and this will be negative or Q bar. Is it correct or not? Let's see the summarization of the table. Terbalik betul lah. Okay. So it's correct. So you can see here, I did the correct versions. Mana? Okay. For my counting up, and then this is my counting down, this is my positive clock, this is my negative clock. I just want to remember these simple things. So I know already this is table that I need to refer. 3-bit countdown, and this is negative. So I need to refer to my negative table. Countdown is connected to my Q bar, previous Q bar. So I just draw a simple flip-flop that I remember for my JK. First is my FF0, FF1, FF2. This is my J0, K0, J1, K1, G2, K2. I have Q2, Q1, Q0. Okay, done. And then after that, I need to connect everything with my high input. So this is my high. And then for starting, I have negative, I have negative, I have negative, and the start will be connected to the clock. And my J will connect to the similar input, which is high. Now how to connect? This is my normal JK flip-flop, and about the negative clock there, I need to remember like this. So it will be look like this. Done for my connection of logic symbol. So it's already done there. So I got 4 mark for my drawing. So it's all correct. So what your lecturer will look into first on the flip-flop, is it from LSB to MSB or not? What is the connection for your J and K? If you just draw this but you didn't put high, or you just left it to be empty, so we don't know what is the input that you are assuming. And the first clock should be connected to the clock, and this must be all similar. If it is negative, you need to have bubble. If it is positive, you need to remove this bubble. And another one is in terms of the connection. Is it correct or not? Okay, after we have done this, we need to draw the clock. Following the equation, it asks you to draw 8 cycle. So you draw until 8 cycle here. Negative clock, you draw the negative arrow here to help yourself to see it clearly, and also help your lecturer while marking. What you're going to do, you're going to do a toggle because your J and K is equal to 1. So you draw until you meet your first negative clock, you're going to toggle. Until you meet the negative, going to toggle. Until you meet your negative, you're going to toggle. Until you meet negative, you're going to toggle. Done. After that, because you can see it's going to have your Q bar for the next flip-flop. This will be your next clock, your CLK1. But you don't know what is the output. Of course, it's going to be toggle from your Q bar. It's going to be like this. You just toggle the output. When you have done, you're going to continue with the error also. Negative, negative, negative. Oh, salah. Negative, 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 negative. So you're done with this. This will be your next clock, right? So you will do the toggle when you meet the negative clock. So you can see here, whenever you meet your negative clock, you're going to toggle. Done for your second flip-flop. Your next flip-flop, which is flip-flop Q2, it is going to depend on your Q1 bar. So you need to know the value first. You need to toggle from above, from your Q. So you toggle and you draw your negative clock, key. Done. Here will be continue until you meet your negative clock. Toggle. Your negative clock, toggle. Finish. So each of this cycle, you need to put the value of Q2, Q1, Q0. This one you need to ignore. 0, 0, 0. For cycle 2, 1, 1, 1. For cycle 3, 1, 1, 0. For cycle 4, 1, 0, 1. For cycle 5, 1, 0, 0. And continues. You're going to get all the counting down. And lastly, here you have 0, 0, 1. So you just represent it to be in your stat table. 0, 0, 0, 1, 1, 1. Just now what I draw last for the last one. Okay. And you can see it continues to next 0, 0, 0, which is goes to your initial back. That's why you will have this. After you reach this part, which is stat 7, you go to the stat 8. This is your stat 1, stat 2, stat 3, stat 4, stat 5, stat 6, stat 7, stat 8. And then after that, you can see it's going to repeat back to your initial value. So that's why you're going to go for here. Repeat several times. Okay, any question for your counter? Any question for your counter? Okay. Okay, next we're going to look into unsynchronized ticket counter.
Doctor,
Yes?
why, like, just now I see the statement is 000 that you write. Or just now, but why in the table?
0, 0, 0. Yes, supposedly it should be 0, 0, 0. I think this one supposedly it's going to be 000. Initial also 00. Wait, because this one is negative clock. You're going to toggle here. 000. And lastly, that's why just now I get at this part is 001. Yes. Where is it? Okay. Clock pulse. Initial is 000 1. Yes, clock 1 is supposedly 000. And then it's going to be continuous with 111, right? Until here it's going to be 001. 9 it will be 000 if you try. So I guess this one is teranjak satu. So supposedly you need to draw basically similar. I check for another answer. Wait, just now we have 00 00 cycle 1 clock pulse Q1 Q2. Yeah, supposedly we need to look into directly at this part. This is our value for our clock. Let me double check here for the answer, okay? Thank you for asking me for this one. Because supposedly you need to look into the clock pulse and it should be similar to whatever value that you have in between. Okay. Okay, other than that, do you have any question?
No, doctor.
Okay, let me proceed with our unsynchronized decade counter. So there is also possibilities. You can see here you should have the transcended sequence. The maximum number normally for your counter, it should be to the power of n, the number of your state. If you have 2 bit of numbers, right, 2 bits, you're going to have to the power of 2 because this is numbers of bits that you have. Then your state is 4. If you have 3 bits, your state is to the power of 3, your state will be 8. However, it can be designed less than to the power of n. Let's say for this is 4 bits. So supposedly you're going to have 16 states. But you can see here, until this state, you directly jump to your 000 back and continues. So it's called as transcended sequence. You not go for all full state should be you do for your counter. So this is the common asynchronous decade counter that you normally meets later on is 10, which is modulus 10. Later we will see for the next slide. This one we call as the decade counter. Okay, this is decade counter. It will force the counter to cycle before. You can see before you go through your normal state, it's directly go to the initial point and it's force you to cycle back. This is your decade counter. And you can have the modulus 10 as mentioned in these sentences. Normally for your transcended sequence or decade counter, this is the frequent use. Okay, if you have modulus 10, what will happen and what is the difference between decade counter and also your normal counter that just now you what is the difference between your ripple counter? This is your ripple counter, which is also similar to, can see here, Asynchronous counter, also known as ripple counter. This is ripple counter or asynchronous counter. But now when you have something that forces you back to the cycle before you have the full normal stages, we call it as decade counter. And for decade counter, the only difference is when you need to add NAND gate. The rest is similar. You can see here it's all similar. But then if you have the decade, you need to add NAND gate, and this output will be connected to your clear. So this is in terms of new connections that you need to look into. Okay. Then how you going to see and put the inputs for this NAND gate? Because your output is already fixed. It's already fixed to be connected to your CLR. Okay, your output for your this NAND gate is connected to the CLR, all your flip-flop, and it fixed for this part. But for your input there, for your input for the NAND gate is depend on the numbers of modulus. Now our modulus is 10. If you convert to binary, you're going to get 1010. This is normal conversions of decimal to binary. If you still remember your numbering system, when you convert, you get 1010. And if you still remember your SOP, POS, whatever things that Boolean expression, when you have 1, then you have the connections. So that's why you can see here, this will be your Q0, Q1, Q2, Q3. My Q3 are connected. My Q1 are connected. That's why I can connect here with my Q1, and another one is Q3. Okay, next, we see another example. Ignore about this first. For modulus 12, what will happen? I already mentioned everything is similar. The output of the NAND also will be similar. But the only difference at the input there. When I have 12, I need to convert to my binary. I'm going to get 1100. Here is my Q0, here will my Q1, here will be my Q2, and this is my Q3. I can see I have connection for 1 and 1 here, Q2 and Q1, Q2 and Q3. So this is the connections that I need to add for my apa tadi nama dia? Decade counter. You know that in the early stage, I said I didn't like to remember the terms, right? So it is always be missed for me to remember the terms. Okay, this is the connections that you need to add for the decade counter. If you have something like maybe, okay, let's go for our counter. Ripple counter here. Okay, maybe this is my asynchronous counter. I need to convert it to be my decade counter for modulus 7, let's say. So what I need to do is I'm going to convert this to be my binary. I'm going to get 111. Betul tak I convert this? Yes. After that, when I have this 111, I need to draw my NAND gate, and this my NAND gate will be connected to my clear here, CLR, and I'm going to have 111. This is my Q0. This is my Q1, this is my Q2. All got connections. So I'm going to connect this to my Q0. This will be my Q1. This will be my Q2. So this is now I change from my SC counter to my decade counter. The only things that I need to change. Okay, the rest is also similar. Okay, when you have the decade counter, it's going to be some things that unusual for your timing diagram, because when you have this modulus 10, after you find this, you can see, let's say for modulus 10, this is your modulus 10, okay, until 10, it will force you to go back to your 0, 0, 0, 0. Okay, after that is going to force you. Okay, that is the first thing that you need to stick on your mind. Force. Here is your normal timing diagram. Okay, this is your normal timing diagram. You're going to have for this question is going to be counting up, so it will be in this question it will be negative clock. I can see here. Okay, I done mark with my arrow. So my Q0, I'm going to toggle when I meet the negative. When I meet negative, I'm going to toggle. So I will get this similar until my until my cycle 10. I'm going to do and draw it like this. So there is nothing happen, not different between my blue color with the green one. Okay, second, this will be my next clock right. So I'm going to do toggle when I meet the negative. Ish. Padam semua dah. Okay, I'm going to do like this. You can see there is a slightly different between my drawing with the green color at this side. But it's okay. Let it be like this first. And I do my negative clock next. This will be my next output for Q2. So similar. I'm going to toggle only negative, right? So at this part also, I'm going to get like this. So there is two things that different, because supposedly at this stage, for your normal AC counter, you're going to do toggle at your negative clock. Supposedly after you have 0, you need to go to 1, isn't it? Because you need to go for 1010. Okay, supposedly you're going to have like here 10 1010. Supposedly for your state here, you're going to get 1010. But after you get 1010, your normal SC will be go to 1011, supposedly. But you have the force to go to 0000. That's why it's going to force you. This CLR will force you to do it. It called as a glitch. to force you to go back to 0, 0, 0, 0. So suppose your answer here will be 0, 0, 0, 0. When it push you, when you have like 1, suddenly you have glitch or you're clear, it's going to push you to 0. Then you do here. There is nothing different you can see at this from 1 to 0 because it is not like a normal process of toggle. But for this side, okay, I delete first. For this side, when you already go up, because your normal unsynchronized will go up first, right? Go up first, then suddenly it asks you, clear everything, 0, 0, 0, 0. Supposedly it's going to be force you go up first and then suddenly there is a force, that's why you go down. We call as a glitch. It's very small, we call it as nanosecond. So maybe I can draw here. You supposedly you're going to go up for your normal and synchronize counter, because at this negative clock here, you're going to do toggle from 0 to 1, right? So you already toggle, but then there is a glitch asking you to reset and force go back to the initial. So you will drop. You will drop. You will drop here and continue to be 0, 0, 0, 0. This is the things that it want you to do, to reset all the value here to be 0, 0, 0, 0. And for this part, when you have this, it's called as glitch. It's very small nanosecond. For this, from high, it asks you and force you to be 0. You can't to see the glitch, but in a small frequency, here, small nanosecond here, you already go to 1 first, but then it force you back to 0. That is the things, but you can't to see a glitch like up to down because you start already from up. But when you start from down, you supposedly goes to up, suddenly it force you to down, then it called as a glitch because this one is very small nanosecond. Okay, so this is happen. This is when you have mode 10, because after 10, after value of 1010, you push it to be 00. If let's say you have the example to be at 11, 12, from here it push you to go back. We call as mode 12, right? So for this example, mode 12, after you meet 1000, you're going to push everything, go back to force it to be 000, then it's not going to be at Q1, the glitch anymore. So let's take a look what is happened. We're going to have the normal things, negative clock, and then you're going to have the toggle thing you can draw. I assume it's to be similar. You can see everything is similar. And then this will be your next negative clock. So you draw the negative clock there, continuous toggle, and this will be toggle at this part because this is negative clock. Now my next negative clock will be here. Okay, I'm going to draw from 0. I'm going to toggle here again. I meet my negative clock here. I supposedly toggle. Okay, I left this first. And this is my negative clock. I'm going to toggle. Okay, these two supposedly the answer for asynchronous counter. But when I have the mode 12, I need to pause my CEAC to be down directly to 0000, when I meet at my mode 12 there. So you can see here it will glitch to move to force you to be zero every single thing here. That's why you're going to have from up there it's force you from up there it force you to down. Wala, warna lain. From up there it force you to down. So you're going to down here and start with 0 0 0. We have a glitch. And for this part, from up it force you to down. So it's going to be here. So here we look like as a glitch because from down it goes up as an unsynchronized counter, but because it is mode 12, you're going to force it to down. We can see a glitch there. So it's depend on the equation. You need to see carefully, draw the timing diagram first, and then after that, what I'm doing, you draw. It's basically similar first as asynchronous. Then you see which mode that you have. If 12 at this side, you need to go to down. Everything need to go to 0. Here need to be to 0. So when it need to be a 0, it goes to like this. But this part you can see it going to be glitch. So any question? So there is the advantage and disadvantages of your SC, asynchronous counter. That's why you come out with your decade counter here. So the advantage of asynchronous is simple in step, but there is disadvantages. So disadvantages is when you have a delay. Let's say you have here on the delay, assume 3-bit counter using flip-flop with a propagations delay of 50 nanosecond when you have low frequency. You can read this, but when you have all the information, you're going to have each state are having the delay of 50 nanosecond. At this first stage, you can see you're going to have the delay, small delay, 50 nanosecond. All together for your cycle, it will be 1000 nanosecond. And because of the delay, supposedly at this part, you're going to change, right? Because small sangat, I draw dekat sini. Okay, this is your negative clock. This is your negative clock. Your output, supposedly, you're going to have directly changes at the specific line, isn't it? At the specific line. But when you have delay, it's going to be delay a few 50 nanoseconds. Then it's going to be here and it will be like this. It will be like this. You can see there is a difference between each other here about 50 nanosecond because it delays. Supposedly it's going to change directly at this time, but it's delay a few seconds, similar to this part. For the delay, sometimes it's going to affect your value if the delay is too big. Let's say you have delay which is too big here, then suddenly you change at this part and you change at this part, which is supposed you need to change here, right? You need to change at this part, but it have delay. Your value will be affected. Sometimes it's affected because the delay is too big. But if the frequency low, which is only small, then there is no effect on the counting sequence. You're going to have the similar value at this specific cycle. At this specific cycle, your value is similar on your counting, synchronous counting. But if you have like high frequency, your delay, uh, your delay is still 50 nanoseconds, but you have 50 megahertz, which is about your value for your tempo here, which is 100 nanosecond only. You can see if you have 100 nanosecond, but your delay is 50 second, which is half. Okay, half from your cycle. But this one 50 nanosecond delay, but your cycle is big. That's why you just affect only small things. You can see here it's similar to like when you have 100 ringgit, but suddenly your friend are taking RM50. How many you have left? 50 ringgit only, right? But similar value for the delay, RM50 you need to give to your friend, but you have 1000. This one 1000. So you just effect small, you only you now have 950. So that's why it doesn't affect the value. But when you have a small cycle which is high frequency, this the value of delay is similar. You're going to see that the value of your cycle will be affected at this certain level until because it's going to effect, right? It's going to teranjak and suddenly it's effect. Supposedly you're going to have like 100, but it's directly jump to another value because of the delay. Okay, so this is just to see what is happen when you have a high frequency and low frequency. Sometimes your value must be affected. Effect of your propagations delay when you have the delay for your low frequency and also high frequency. Okay, next, one more thing I asked you to remember yesterday. There is two equation. This is first equation and also another equation I asked you to remember. If you were given with direct question like this, you were given with the value of mode. You just apply this value here. You will get the number of flip-flop, which is this big N here. And your recycle up counter jacket is for 40 nanoseconds. You're going to put here. When you have the value of N, you just apply to your 5 here, and this will be from this value, then you will get the maximum number of your frequency. But sometimes you will given with the frequency, you were given with the value of flip-flop, you've been asked to calculate the TPD. But sometimes you were given with all this value, but you need to find the N. So that's why I asked you to play around with the equation. This type of question will be come out to your final exam. So please make sure you remember the equation, and it's not going to give directly similar things, which is asking you to find the frequency instead is going to play around with the value. So you need to play around with the equation. Okay, we finish with our module 8A. Any question? So later on, after this, we will meet our module 8B before we go for final module 9. So from here, you can see you have much more advanced, which is you're going to also apply your K-map later on. You're going to have bigger table, transition table. You have the present stat, net stat, and the JK transitions table. So a lot of things. Before you're going to go deeper, please make sure you understand the simplest table we have in our module 8A. Before this, you need to understand also how to draw the timing diagram, how to draw the state diagram, how to draw the table, and about the basic things here also. You're going to apply for your module 8B. So a lot of steps. You can see step number 1, you need to draw the circuit, input, output, and then you need to draw the state diagram. Next, you need to create the state table. See, vice versa. Just now you need to draw the state table, but now you need to draw the state diagram first. And then you need to create the flip-flop transition table, the new things that you're going to meet. Use the K-map to derive the logic equation. And lastly, implement the counter. So maybe before our next class next week, please make sure you read and go through first. Then we will discuss together. Okay? Any question? Silap pula. So any question? If there is no question, we can dismiss. Go and meet your group member and start doing your project. Don't wait until next week and next week, because you have only a few weeks more. Finalize your scenario, which scenario that you want to do, and then you discuss about the you have what scenario, which scenario. You have a few example given already. You can have parking lot, you can have the bomb, you can have lift. So all that, if you find in the Google, please save the references. Okay, we need to start now. You have another 30 more minutes. Go and meet your team member and do the discussion. Thank you for your participants. Meet you again next week. Bye-bye.
Thank you, Doctor.
Okay, bye-bye. Okay, bye.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, doctor. Okay, bye-bye.